Okay, we are continuing our way in defining or characterizing different forces that we encounter in mechanical systems. Another one that we encounter frequently is the force of an elastic element or force of a spring. Let me actually write it down. Force of elastic elements. So consider an elastic thing. A coil spring is one of them, rubber possibly. What we are dealing here, and that is the simplest case, we are characterizing force of a linear spring. And that is a very good approximation for like the coil springs that you use in the mechanisms and machines. They are linear to a very good approximation. What linear means is that when you have a spring of some length, let's call it L naught, if you stretch the spring, let me make a bit of space. This one. Make it longer to some length L. The force that is developed in the spring, let me write it this way, force of a spring is proportional with some constant value to new length minus the original length. This one is often called resting length, where is the T? Length. And that is the length the spring has whenever it's relaxed, whenever there is no just leaving the spring on the surface of a table, for instance. As you stretch it or compress it, let me draw another case when L could be in compression. Let me give a bit more space. And that is the force. We should be careful what we really define as this force. This is the magnitude of the force. But we also need to worry about its direction. For the springs we are dealing with, the direction of the force, so the force develops in a spring, as you stretch it, is always along the main axis of the spring. But whether it is compression or tension force depends whether you have stretched it or compressed the spring, whether the length increased or decreased. And going back to the third law, Newton's third law, there's a force, the spring is pulling the system, and there is, what is happening? There is a force U pulling the spring. So these are two separate forces on two separate bodies. And you should be careful which one you define as your force. In that case, one of them would be plus this, the other one would be, not that. One force would be plus in the pulling direction, the other force would be in the opposite direction, for instance, in the spring. So what we often care about is the force that the spring applies to the other bodies, and that is Imagine you have another body. What we care about is often in the free body diagram, we isolate this. There is the force of the spring, and this one, this force, if you stretch the spring, so if you move in that direction, the force becomes in the opposite direction. So often you will see that forces, the magnitude, is in the opposite direction of K L minus L naught. So this minus sign comes from the direction of the force relative to the positive assumed direction of elongation. You can all, I didn't mention this, K delta L, or change in length, is often described by delta L. So to summarize, force of a spring is along the main axis of a spring. If the spring is linear, the magnitude of the force is proportional to the change of length relative to the resting length. And depending on the direction of the force, either compression or elongation, you need to take into account the correct sign and direction. So that is all I wanted to say about the spring. Let's do friction, and that would